G'day, my name's Nicky Ringland. I'm a product manager at Google working in Google Cloud, and I'm joining you from the Gadigal lands of the Eora Nation here in Sydney, Australia. Today I'm going to give you an overview of dependencies, specifically understanding them for fun and risk mitigation. Yes, that's the one. So just quickly, at its core, I work on a team called Open Source Insights. And what we do is get an accurate dependency graph model for open source ecosystems. We aggregate information on dependencies, security vulnerabilities, licensing, other package health metrics, enabling tooling that supports building safer and more robust software and products. Because it turns out that, just like old Captain Napkins here, dependency problems can get pretty hairy. But here you are, working on your awesome project, and you find yourself installing a dependency. Great! So much progress, you're flying, fantastic. But what even was that? What did you just install? And we may as well get the requisite XKCD out of the way. Chances are, yes, your dependencies look like this. We've got a live image right now. And there are some pretty good reasons that we've ended up here. It turns out that creating software has become more and more complex, and developing using open source libraries lets developers build things faster. Organizations can be more nimble, we can all be more productive. Essentially, open source stops us from having to reinvent the wheel, which is a great thing. So here we have your nice, tidy dependency tree, right? Well, it's a bit more complicated than that, it turns out. Let's take a step back though. Let's take an example using software dependencies. So you're developing a package A, and to do so you depend on several other packages which provide some functionality, and they in turn might depend on more packages and so on. But if there's a problem deep in your dependency tree, say a vulnerability or a package with an incompatible license, that might have consequences for your project, because the problem might not be isolated to package K. It could affect I, it could affect anything that depends on I, and worst of all, it could affect me, because of a problem in a leaf package I've never even heard of. And if your problem with K is a license incompatibility, your whole tree is infected by this license. So as a quick overview, this is deps.dev. I'll give you a bit of context with this, and then we're going to get deep down into some technicals. So let's say we're interested in a particular package called Express. And we can see information about this package. We can see whether it's impacted by security advisories, what its dependencies are, what its licenses are, some information about its owners, any links it has, and any event history. So this might come up with ownership changes or versions being released. We can also see important information here from the Open SSF scorecard, which is a really fantastic initiative that I will talk about a little bit later in this talk. But let's say I'm not actually using this particular version of Express, but a slightly older one. I can look up that version and find out that it is actually impacted by an advisory, not itself, but in one of its dependencies here. So that seems bad, but I don't actually understand how that impacts me. I can look at its dependencies, look at all of its dependencies here, select just the ones that have an advisory, but here's the nice bit. I can see how I depend on this package that has the advisory affected. That's kind of cool. Then if I want, I can look at this comparison to see what the difference is between this version and any other versions if I want to update perhaps to the most recent version. I can see it's no longer impacted by an advisory, but there is quite a bit of change between the dependencies, so that might warrant a security review anyway. All right, that's a bit of context. Let's get back into the technicals. So here we are, with our tree, with knowledge that we might be impacted by something in it. How big of a problem is this? Well, it really depends. And one of the things it depends on is the ecosystem, because some languages and some package ecosystems tend to use a lot more dependencies than others, and that increases your risk. Now, dependency hygiene is a complex beast because of this. It depends on lots of things how much of a problem it is. Part of it depends on how you count and how you define an average, but more on that later. So some of these languages, in some of these ecosystems, dependency hygiene is really hard because dependency bloat is a really common or unavoidable challenge. For instance, NPM packages seem to rely on an abundance of micro packages where very specific things are in their own dependencies. So this is an average number, give or take, of direct dependencies for an average package in NPM, and this is an average package including all of its indirect dependencies, which usually amount to several dozen to a few hundred total. So keeping track of all of these changes to dependencies and the repercussions of those changes in a graph this size is just too large a task to do manually, because the size of these graphs just means that solutions have to be automated. Now, I'm going to propose this as the modern Rash or ink blot test. So to me, this graph looks just a little bit like an elephant, which is somewhat fitting given that ensuring the security and authenticity of various artifacts in your software depends on, really is one of the big elephants in the room when it comes to talking about software security. But each one of these in this graph, 312 nodes, potentially has several different authors and contributors, and that all builds to your chain of trust. And that's relevant for any project in terms of software security. So those numbers really do add up. As of a few weeks ago, if you were using Kubernetes, you were implicitly trusting not just the 1,000 or so owners and contributors to Kubernetes directly, but also the 13,000 contributors to its 200 or so dependencies. And that is a lot of trust going around. But it's also a really cool thing because it lets you leverage that. So let's just have a brief interlude for some more cross-ecosystem comparisons. Let's look at how many packages there are in each ecosystem. We can see that NPM wins out here with just a swell number here, somewhere shy of 5 million and counting. But each of those packages has a number of different versions, and now suddenly we're up to multiple millions, nearly 25 million for NPM. And if we look at averages, we can see that actually Maven wins out with the most number of versions per package. All right, so let's talk a little bit more about the average package, and there are some rather large caveats here. One of them is counting is surprisingly hard. Averages are tricky. What do numbers even mean anyway? But nevertheless, we persevere. So let's look at the average number of dependencies. Here we have the average number of dependencies for all packages in our system for each of these various different packaging systems: Go, NPM, Cargo, Maven, and PyPI. So that's for Go, Node JavaScript, Rust is for Cargo, Maven is Java, one of the large Java repositories, and PyPI is for Python. We can see that there are, on average, a large number of dependencies. But there's more to it than that as well. Those numbers on this slide are averages, and there are an awful lot of packages that have no dependencies as well. So in fact, in Python, it's more common than not for a package to have no dependencies, which means that the ones that do may be skewing the average there just a little by having lots of dependencies. But if I'm pointing fingers, it probably wouldn't be in that direction. So what even is average anyway is a very valid question. So let's talk about these numbers were from all versions of a package, but that includes even the very early versions of packages that were released, and it also skews our numbers towards packages that have many versions released. So if we instead look at only the most recent version of a package that's been released, we can see that it's a slightly different story, but these numbers also seem a little more tenable or realistic. But just for a cross-check on our numbers, I've pulled in this graph from GitHub's 2020 State of the Octoverse report. Now this looked at all projects rather than only packages, and it also looked at lock files. So the numbers for some of the systems are perhaps based on smaller sample sizes for language that don't have lock files. But here we can see that the median number of dependencies for NPM is just outrageous and accurate. So one of the things I alluded to earlier is that the order of magnitude difference here between NPM and other language ecosystems is driven by NPM's philosophy of micropackaging. So this is where even like one-liner functions will be taken on as dependencies. And that, together with the small size of the JavaScript standard library and the complex environment in which JavaScript is often used in the web browser, that's a factor here. But this also includes things like whether your build tooling or your dev dependencies are included. So what this is saying, though, is that 50% of the JavaScript repositories in GitHub have more than 683 dependencies, which is truly terrifying. But what about you? How much of a problem is this for you? That really depends on what you're building and understanding what's going into it. Answering the question, do I have too many dependencies? Because that is relevant for a whole bunch of different things. So the number of dependencies matters for your build times, your download or your checkout times, maintenance, testing, deployment, updating, security, licensing, compliance. These are all things that are affected by the scale of your dependency graph. And you need good information supported by good tooling in order to understand and make good choices about your dependencies. And when it comes down to it, it's not just the number of dependencies either, because unfortunately your dependencies don't look like this, they look more like this, and that's just much, much harder to understand. So here, I'm looking at mean dependency depth. So how deep is that dependency chain that something could be hiding in? And we can see that, mostly what I see from this graph is that averages and numbers are hard to interpret, as I alluded to earlier, hard to count as well. So let's look at the maximum one, because much like Big O notation, I like a good scary story. And we can see here that the maximum dependency depth across languages is quite alarming in all of them, but especially in NPM here. What is going on with this one? I'm so glad you asked. So I dug into it. It turns out that this is a particular package, which is a TypeScript object going by its definition. So the package seems to provide a bunch of utilities for functional programming in TypeScript. And the interesting thing here is that it's actually bang on average for whatever average means. It's only got about 6 direct and 80 indirect dependencies, which you'll remember is very within the scope of normal for NPM. It's not the most popular of packages. It's got a few hundred downloads a week, but that's not why it's curious, right? It's curious because it has a dependency chain that is 58 deep. So this is not an outlier. This is a resolution bug that's happening in what I'm going to call it a frill neck lizard, in this beautiful frill of a dependency spiral of doom. And let's get on in that, where each version is depending on lots of different versions that are depending on the slightly older versions of those, and it's interlinked and so on. But you will be pleased to know that this spiral of doom has been fixed, and this is what the most recent version's dependency graph looks like, which is much more easy to understand. So it's also relatively easy to end up in a situation like this with this package spiral of doom in your dependencies. And it's often, in that case, very difficult to notice something lurking in them in the deep, deep down. And this is really a problem because we know that nearly 40% of all published NPM packages depend on code with known vulnerabilities. Now, those vulnerabilities might not actually make the code unsafe to use. They might be alerts for regex DDoS in a testing framework, or maybe it's a vulnerability in a part of the library that you never actually use, but they all need to be checked. And if you remember those graphs, the scale of this problem is monumental. But there's also another dimension to it as well. This graph isn't static. It changes frequently. In fact, between 10 and 25% of all published NPM packages have a change in their dependencies every single day. And that rate of upstream change is ridiculously hard to keep track of. So even what I mean here is that the dependencies that you rely on can shift like sand underneath you without you necessarily noticing. Because even if you haven't changed your direct dependencies, one of them might have had an update available that might get pulled in automatically depending on your setup. And that new version might pull in a new package, which in turn might pull in other new packages, and they might not have been through security or license checks, because remember, this has all happened without an active change in your project's dependencies. And we see this happen a lot. In fact, every day, 40,000 packages on NPM had a change in their dependencies that caused a change to their license set or their advisory set. So that's a change that adds or removes a license or adds or removes a security vulnerability. And that's every day. So here, really, I'm trying to get that it's critical to understand what's in your dependencies and how they interact with each other, and identifying things that are surprising in them is also really important. I've been picking on NPM a little bit. I don't actually mean to. These are all big, scary numbers, and it's not surprising because big, scary packaging systems have big, scary challenges. And actually, in many respects, NPM are leading the way in a lot of tooling to help developers face these challenges. The NPM packaging system has a tool called NPM Audit to help with this. And this is a really good way of discovering the vulnerabilities that you have in your dependencies. But what do you do then? How do you know exactly and clearly what course of action you have, how you depend on it, whether it's important, whether there are options? And some other systems are also developing similar tools, which is great, and I'm really looking forward to them being available. But ultimately, there will always be this upstream and there will always be change. And while change is inevitable, it's not always good. Which brings us to some vulnerabilities, advisories, and bugs in your code section of the talk. But as I alluded to earlier, there's more to dependencies and making good choices about your dependencies than just avoiding vulnerabilities, because, well, we can't do that for sure because they change. Vulnerabilities aren't the only thing you want to consider when deciding whether or not to depend on a package. And here, the OSSF scorecard is an initiative of the Open Source Security Foundation, which is a cross-industry collaboration to involve the security of open source software. And the scorecard defines a set of metrics and provides automated security scores for them. And the goal is really to help automate security posture analysis of OSS and proactively help improve these critical open source software packages and components. So some of the metrics include things like whether or not there's code review, whether dependencies are released, whether release artifacts are signed, and I encourage you all to really go and look at this project and see if you can contribute. This information is really useful for developers and organizations to make a better judgment call on whether a package should be trusted and depended on. Because it's more than just whether, in fact, vulnerabilities that are fixed are a great metric to whether a package is healthy and can be trusted. All right, so on with the vulnerability show. So here we have the timeline of a vulnerability, the advisory life cycle, if you will. So vulnerabilities are reported through advisories, which are available from several public databases. There are either individual packaging systems, NPM and Go have some of them, or there are also aggregated databases like the GitHub advisory database. So vulnerabilities are scored for severity based on a few factors, including how difficult they are to exploit and the impact of any potential successful exploit. So here the life cycle is that a vulnerability is identified and reported. It's perhaps introduced at some point and then a long time later identified. A maintainer then looks at it, releases a patch, ideally. Your security tooling would then tell end users about a security update, and then developers update to the fixed version, and everything is happy, right? So let's take another look here. The problem is that when there's a vulnerability, it affects a package, or particularly a version of a package, or maybe even multiple versions, and it might be the most recent versions, or all of them. Now, when the newest release is patched, the older versions still hang around. So you end up with situations like this, lower level, depending on where in the vulnerability life cycle this package is. And these older versions are still around. So it's really important to know about which version of a package is affected and which isn't. And here I want to have a good shout out for vulnerability data sources that make this really easy to identify. If you're not familiar with open source vulnerability format, I very much encourage you to take a look at the schema. But essentially, developers here want to know if they're using a package, a version of that package that's affected by the vulnerability. That is, the specific version of the package they're using is affected. But some of the older vulnerability formats, like CVEs, typically only include whether or not a package is impacted, not which specific version. And that means more noise than signal, which in turn makes people ignore vulnerability warnings, which is a bad thing. So we're really happy to see and use the shared vulnerability format linked in the slide here, because ultimately having really precise security information is critical to enabling developers to understand what needs to be fixed and to build safe software. Okay, so your dependency, you found out that you depend on an affected version, a vulnerable version of a package. Whether you have a beautiful dependency tree or more of a spiral of doom, what next? Now you need to figure out whether there is a fixed path of patches from that vulnerability to you. Now, if the vulnerability is one that you directly depend on, you can change it. But if it's several layers down, you have to hope not just that it itself has been patched, but all of the intermediate steps are also updated. And that doesn't always happen. We don't know how long this takes, how often it takes, how often it actually happens, whether it gets stuck. It's really actually difficult to know how many advisories are mitigated, because what is solved? Is an advisory solved if affected versions are still out there being used? So we found one recent advisory that had a lot of dependents and a lot of versions, and some versions had been patched. So the particulars, this is a fairly recent one, and we looked into it. Older versions, between 0 and 4, have not been patched, but the two most recent major versions, 5 and 6, both have patches available. So we were curious about how long it takes for people to move their dependencies from an older affected version to one of the new patched versions. And they did, which is great, but not all of them did. But it's really tricky to say whether or not this is a success story. This isn't the whole story. This graph that is still dominated by blue rather than orange, it would be great to say suddenly all of the packages that use this, the affected versions move to new versions, but ones that are still out there that were released before this even was a problem aren't going to be yanked. So how do we know how people are using fixed versions? How many people are using a version that isn't yet fixed? How do we accurately count who a user is? And maybe some old versions will continue to depend on a bad version, and that's normal, because if they're abandoned, then they don't need to be used. So we looked into some metrics. I would love to see more about this from a downloads perspective as well, how active the code base is, but we just don't have a good answer here. And that's part of the problem. When we're talking about vulnerabilities, it's tricky to know how big the scope of the problem is. All right, so let's talk some more about graphs. We have our dependency graph that doesn't look like that. It looks like this, except it also doesn't look like this. It looks like this. Really, our frill neck lizard swarming mess is more accurate because there isn't actually one graph. And I know I've said that before, but this is a new way that there's a not one graph. It's all messy. The true dependency problem isn't about making dependency management easy. It's about understanding what your dependencies are, where they come from, why they're there, and the consequences that brings. But this is a much harder problem than realized because there are so many factors that affect the answer. So when software is built, the set of packages, or actually the versions of packages that are included in the software, have to be evaluated. And the resulting dependency graph describes all of the versions that are built, that are used in the build. And the inputs to that process include things like the kind of build. Does it include testing? What are the target operating system and architecture? The source code, metadata, packaging metadata files such as lock files or package.json, go.mod, the source code, obviously, and metadata for all of these dependencies, and also the build tools. Now, those build tools for whatever system have to gather these inputs and use them to compute the dependency graph by evaluating any constraints created by the dependency requirements. So you might have requirements saying I need a version less than 3 or exactly equal to 2.0.1 or greater than 3. It could be environmental constraints, things like this is a build for Windows, what kind of build it is, build the tests as well as the software, or perhaps build specific considerations. In this case, perhaps like the binary must be minified. So based on these choices, a set of versions of each package are possible versions that satisfy those constraints, and those are then chosen. But which one to pick? Do you pick the newest version or the oldest version that satisfies these requirements? It turns out that that's actually a decision made by the tooling that you're using to satisfy, to build your tool. And that changes from ecosystem to ecosystem. So Go actually prefers the older option. It's more stable, and that's a useful thing when developing software. But on the other hand, other ecosystems prefer the most recently released version. It has the freshest bug fixes, the shiniest features, also perhaps the freshest new bugs. There's no one right answer here, but these are all decisions that are made often without the developer's input. So one of the questions here is, can lock files help in order to ensure that we're using the right versions of these packages? The common approach of using a package lock file to capture which versions is good, but inadequate to determine this exactly, because it only holds one evaluation, usually used as the input to a build, and then it's often rewritten as a result of evaluating the build itself. It represents just one build under some conditions in some environments in some particular time, because it's not the dependency graph, it is just a dependency graph. And using it as the sole source of truth can be misleading for a few reasons. The dependencies could have changed since it was computed. Some versions might have been yanked or deleted. The code might have changed since it was computed. Maybe the lock file changed, but the maintainer didn't commit those changes. Or the environment was different, that you're building in is different. Or maybe the purpose of that build could be different. Maybe we don't need tests, or we specifically do. And when we're talking about SEMVer requirements, which is the requirements that determine whether or not a particular version is included, between ecosystems is a bit of a mess identifying what is allowed, what isn't allowed, what the meaning is, and there are several inconsistencies there as well. So how do you get from these requirements to your dependency graph? Let's take a look. So we've said it's not the graph, but a graph. So the goal here is to say, how many graphs are we talking about here? But we'll walk through step by step. So to import dependencies, essentially you need some tooling. And tooling is necessary because often, if not always, the language implementations are oblivious to the notion of versioning or even third party. So the Java virtual machine retrieved bytes for a class through Bootstrap class loader that loads from a hierarchical file system. For JavaScript, Node.js loads from cascading local node modules folders. In these cases, the tooling and not the language implementation performs the dependency resolution and also the bytes downloaded. So popular tools are Maven for Java, NPM or Yarn for JavaScript, Cargo for Rust, NuGet for C#, pip for Python, and Go tools for Go, etc. So in this example, we're going to use Node.js as an implementation of the JavaScript language and NPM tooling. So Node.js will transform this the import string literal into bytes for reading from a cascading local node modules folder. And the creation of these cascading node modules folders is left to the tool we use here. It's NPM. And this NPM tool doesn't read the source files that contain the imports. For NPM to operate, the direct dependencies are listed in a file named package.json. Now this file contains, amongst other metadata of the project, dependency information in the form of a mapping between the import string literal, the third-party package name, and a version range. And it's important to note here that there are two unknowns, the origin and the version, as only a requirement is provided. It leaves a degree of freedom for the version to be selected. And resolving these unknowns, and particularly deciding on the version, is the crux of dependency resolution. So starting from this description of dependencies, NPM performs the dependency resolution and ultimately determines that color, in this case means version 3.0.1 of the D3 color package located at registry npm.js.org. The origin, or the registry, is set up as a configuration for NPM, and NPM retrieves from there the list of versions and decides that 3.0.1 is appropriate based on the required range of greater than 3. And so we see that the node modules folder has been created with a color subfolder, and this satisfies what Node.js expects for transforming require color into bytes. So we also note that NPM created a packagelock.json file that contains the resolution's details, and this could serve for pinning dependencies if that's something we were looking into. So we've got a graph. Hooray! This resolution's outcome is conveniently represented as a graph, here with vertices representing the effective versions selected, and the edges representing the direct dependencies, and the edges labeled with that version's requirements. So below, here is the example for the graph for our first resolution. It's worth noting here that D3 Color 3.0.0 could also have been selected, but the NPM tool decided to go for the latest 3.0.1. It's shiny and fresh. So what happens when the bytes that have been retrieved actually contain imports that need to be transformed in turn to bytes? This is what we call transitive dependencies, as opposed to the former dependencies that are called the direct dependencies. So here we'll add a direct dependency to D3 time, and we know that we know has dependencies, and then we'll resolve. we've used the shortened implicit declaration of a requirement here just to make things a bit easier. So we see that we have 2 additional dependencies that we didn't explicitly require, D3 array and intern map. And these are the dependencies of our dependencies, and recursively the dependencies of the dependencies of our dependencies. So here again, it's worth noting that NPM specified versions from the range of acceptable versions. And the result is that Node.js will be able to transform all the require into the things that it will encounter into bytes. Hooray! So now we have our graph representing that happening. So beyond transitivity, what happens if a given package is the dependency of several others? So let's request this as a direct dependency of a different version of the D3 array than the one selected transitively. Well, we can see that D3 time shares this version, 3.0.0 of D3 array instead of 3.0.1 as previously selected. That's great. But now what happens if the requested versions are incompatible, if those requirements are incompatible? So here, NPM selected 2 different versions of D3 array and stored them in a cascading node modules folder in such a way that Node.js will select the correct bytes when transforming require D3 array, depending on where that transformation occurs. That is to say, where the current compilation unit is stored in the hierarchical file tree. So to complete our example, and we can add another dependency to D3 array under another name and observe that it transitively includes the selection of a lower version of intern map, in this case 1.1 rather than 2.0.1. So this is the resulting graph from that requirement. So suppose we decide to change the import name of the newly added dependency from array to slice. Would that impact the resolution? Yes, it does. That's interesting. So it turns out that because this implementation of NPM treats the dependencies in lexicographical order and stores the bytes of intern map 2.0.1 at the top level of the node modules cascade, forcing intern map 1.0.1 to be stored under slice, because slice can't use version 2.0.1, this has impacted the resulting resolution tree. So what other things could impact this? Well, what if we use a different version of NPM? Yep, new version, new tree. This new version of NPM is not impacted by that change from array to slice of the imported name. What about another tool? What if we use yarn? Yep, so yarn in this case has decided not to share intern map between array and D3 time, between those 2 branches. So here's the thing. All of these graphs, all of these dependency resolutions are perfectly valid. Actually, in this simple example with less than half a dozen dependencies, there are 39,690 graphs that would satisfy all of the constraints. Now, all of these graphs can be the result of a dependency resolution, depending on when it occurred, the availability of versions in the origin registry, and the tooling chosen. And this volatility is a bit concerning. And if it's undesired, then a package lock.json could be used as an additional input to the dependency resolution to introduce some more stability by pinning dependencies. But that's not assured, that's encouraged, let's say. And remember, this is for something that a simple package with half a dozen dependencies. So what about something bigger? What about Express that we looked at before? Now I'm going to call this one a hummingbird, if you'll allow me. Express 4.15.5 has an outrageous number of possible graphs. I'm not even going to try and say that. And what about D3 that we were talking about before? Here I will call this the emu. Yeah. Okay, so that's an outrageously even bigger number. So because an installation tends to be deterministic, to have these large numbers in practice, you'd need to launch as many installations in as many different contexts. So time, operating system, architecture, tool, version. So for time, not all timestamps are equal. The interesting timestamps are the ones where a new version of one of the dependencies is published. So if we wanted to look at what's the chance that you end up with the same dependency as your peer, well, we have a few examples here, and basically it seems like an actual impossibility until you account that resolvers aren't just picking randomly. A reasonable resolver tends to follow two rules: to take the highest Semver version that satisfy these requirements for the versions for the ecosystems that take highest, and also allow that version to satisfy the requirements as long as it's not already installed by some other requirement as per rule 1. And again, time is important here. So if we're looking at taking that into account, if our dependencies, if you're resolving at the same time as your friend, then it's much, much, much more likely that we would end up with the same tree, which is good news, because otherwise software development would be much, much, much more complicated. So here, what I really want to say is the main point here is that it's really hard to know exactly what you're going to get. As we observe with NPM and Yarn, different systems will resolve differently. For example, Maven, Cargo, or Go install only one version per package. Maven takes the dependencies in their order of appearance in the POM file, and Go is oblivious to the order of imports. Go and NuGet take the lowest version that satisfies those constraints, while NPM and Maven take the highest. NuGet, Cargo, and pip use backtracking in their resolution, but Go relies on a linear approach. And these configurations all come into play and allow for a variety of dependency resolution results. Now, a lot more could be said on dependency resolution, but to summarize, unsurprisingly, dependency resolution is critical for dependencies, but it's also implementation dependent. It's performed by tooling, not by the language implementation itself, and different strategies can be used to satisfy a set of requirements. Dependency resolution is not unique, and many graphs satisfy the constraints. And that dependency resolution can be fragile, and any changes, including different tools, different versions of the tools, or things as seemingly innocuous as a change in the name of a package, can yield different results. And that's tricky to keep track of. So I'll leave you here with a few of our favorite graph friends. The swallow on the right there, I'm going to say that's a chicken. And down on the bottom left, we have a worm. And of course, who can forget our fantastic contributor, the swirling massive doom. So today I've shown you a really quick overview of what we're doing with open source insights, a bunch of technical and lots of graphs about how we think that dependency resolution is both really important and really, really hard. We're really excited about exploring this data, how it can be useful for developers and for the open source ecosystem. So maybe you're all too familiar with dependency problems, or just now have become curious about what your dependency graph actually looks like. But with this new view of your dependencies, we'd really love to know what you discover. So you can check us out at deps.dev and get in contact. We'd love to hear from you. Thank you so much for having me. You can reach me at Nicky Ringland if you have any questions, or you can shoot us an email via the contact form on the website. Thanks so much.